fire gets out of control, it is always dangerous and destructive. We're accustomed to seeing the flame rise above the fuel. When a flammable gas or dust mixture is ignited in a confined space, however, the flame travels, sometimes with the violence of an explosion. Scientists refer to the travel of flame in a confined space through a flammable mixture as flame propagation. The laboratory experiments you're about to see demonstrate what happens when flame travels through a mine, a pipeline, a sewer, an electrical conduit, or an electrical fixture. The first experiment is with a percentage of gas air which is just at or a little above the lower flammable limit. The blue dome-shaped flame travels lazily up the tube with no noise. The gas percentage is increased. This time the flame vibrates and makes a noise. Flame has body, and like a thin sheet of metal, when it vibrates, it makes a noise. Again, the percentage of gas is increased. The flame travels faster, hesitates, then rushes to the top with a real whoomph. Since flame has body, it acts like the piston of a tire pump. As it travels, it compresses the mixture ahead of it. This pressure buildup, which caused the flame to hesitate, is often called pressure piling. Again, the gas percentage is increased. Now we have approximately the most violent mixture, so we get the fastest speed, the greatest pressure, and the loudest noise. When the gas percentage is increased even more, the flame travels more slowly. Its shape changes, and so does its color. As we add more gas, the flame becomes more luminous. Note that we have two explosions. Because air was sucked in behind the first flame, a second explosion occurred. This mixture is near the upper flammable limit. Just a tiny ball of flame with luminous particles travels up the mixture. Now, the gas-air mixture is above the upper flammable limit. It burns with a luminous flame outside the tube, but will not enter the tube. These experiments can be summarized by this curve. The horizontal line represents the percentage of gas present. The vertical line represents the speeds or pressures developed. The shape of this curve for natural gas is representative of the common hydrocarbon fuel gases. Just above the lower flammable limit, the flame traveled very slowly up the tube and developed practically no pressure. Each time the gas percentage was increased, the flame traveled faster and pressures increased until about the midpoint. From the midpoint on, speed and pressure became less and less until the upper flammable limit was reached. Then the flame no longer would travel up the tube. We have the same flame speeds and pressures on the rich gas side of the curve as on the lean side. Although the shape of the flame speed and pressure curves for fuel gases are similar, each gas has its own flammable limits, flame speeds, and pressures. Let's apply what we've learned to an everyday occurrence. Have you ever wondered why a flame stays on top of a gas burner, but sometimes flashes back into the mixing chamber? The flame stays on top of the gas burner at the end of this tube as long as the gas-air mixture flows through the opening faster than the flame speed of the mixture. The normal blue flame on a gas burner is really two flames. The inner flame, known as the primary flame, gets its air from the base of the burner. The flame on the outside, known as the secondary flame, gets its oxygen from the surrounding air. If you see a blue flame, similar to this one, at the open hatch of a tank or end of a pipe, don't shut off the fuel. If you do, the flame may travel back into the tank or pipe and cause a serious fire or explosion. If you see a luminous flame, such as this one, it's safe to shut off the fuel because the mixture in the pipe or tank is above the upper flammable limit and will not burn. So that you can see and understand explosions in a pipeline, sewer, electric conduit, or coal mine, different flammable mixtures will be exploded in this 21-foot, 2-inch glass pipe. Every 2 feet, there is an opening covered with a paper diaphragm. These diaphragms relieve the explosion pressures so that the glass pipe will not be broken. They can represent manhole covers in a sewer or stoppings in a coal mine. This flammable mixture is close to the lower flammable limit. The flame travels slowly back through the pipe and makes no noise. Even though there was an explosion, it didn't set fire to the paper diaphragms. Watch how the top edge of the flame travels ahead of the lower part of the flame. Flame travels upward faster than it travels horizontally, and faster horizontally than it does downward. This mixture, close to the lower flammable limit, is ignited by a spark at the closed end. The cold glass cools the hot gases, and the flame moves back. When this resistance is overcome, the flame moves on, hesitates, and moves on again. This mixture is close to the upper flammable limit. Floating like one of Walt Disney's ghosts, the flame travels back through the pipe at about the same speed as it did in the mixture close to the lower flammable limit. The same mixture is ignited from the closed end of the pipe. The flame travels a short distance, hesitates, repeats its action, and flashes out the open end. Air drawn into the tube mixes with the unburned gas, causing flame to travel back into the tube. To give you a better understanding of the speed-pressure curve, the pipe will be filled with a mixture that contains the entire flammable range, distributed through the length of the pipe. Starting at the upper flammable limit at the open end, the flame starts slowly and travels faster and faster to the middle of the tube. Then it travels slower until it reaches the lower flammable limit, where it dies. A uniform mixture seldom occurs throughout a confined space such as a pipeline, mine, sewer, tank, or building. Generally, many forces and counter-forces develop during gas or dust explosions. To show how forces develop during an explosion, let's place a ping-pong ball in the pipe. The ping-pong ball can represent a machine, body, or piece of equipment. The pressure ahead of the flame pushes the ball forward. When the flame passes it, the counterforce pulls it back. If you should be called on to participate in an investigation of an explosion, consider the effect of counterforces on the location of machines, debris, or a body. This mixture is close to the top of the speed-pressure curve. That is, close to the most violent mixture. The flame travels very rapidly. Some diaphragms are ruptured, but others are not. Several were blown out, and others were drawn in. An explosion often blows out or draws in windows and partitions in buildings and stoppings in mines. Flame travels away from the source of ignition. Coal miners have viewed explosions from this position and lived. Miners have been known to outrun slow flame coming toward them, but not one like this. When an explosion travels through a pipeline, sewer, mine entry, or any other long space, it builds up pressure ahead of the flame until something gives, like this diaphragm. This action is repeated time and again in a confined area. All the explosions you have seen have been in quiet mixtures. That is, the gas-air mixture was not flowing through the pipe when it exploded. This time, the flammable mixture is turbulent, like the ventilation currents in a timbered entry tunnel. The flame traveled so fast you could hardly follow it, and the explosion was so violent that it broke all the diaphragms. Explosions involving dust and gas have been studied at the Bureau of Mines experimental mine. Dust explosion flame velocities of well over 3 times the speed of sound have been recorded. Pressures exerted are tremendous. Now you can see what a coal dust explosion looks like. Watch how the pressure wave ahead of the flame blows the dust into suspension. When the flame reaches the dust, it is ignited, accompanied by an intense flame. After the flame reaches the end of the pipe, a second explosion occurs, causing the flame to travel back into the pipe. Mixing a sufficient amount of fine limestone with flammable dust will prevent the flammable dust from exploding. In coal mines, limestone dust is placed on timbers and ledges. See how the rock dust cloud raised by the pressure wave extinguishes the flame. Because of the way flame travels in confined spaces, the following demonstrations show what happens when explosions occur in properly and improperly installed and maintained approved electrical equipment. All electrical equipment used in hazardous areas should be explosion-proof or permissible. The Underwriters Laboratories approve electrical equipment for use in the presence of flammable gases and dusts, as indicated by the label or markings. The Bureau of Mines approves electrical equipment for use in the presence of coal dust and methane. Approved equipment always bears this seal. Since you cannot see flame travel through conduit, the boxes placed at each end have approved glass covers. Now you can see the flame pass the window at the right and then flash at the window on the left. To show you how approved electrical equipment will confine an explosion, both ends are closed. The mixture is ignited with a spark at the left, and you will see it flash at the right. All you heard was a click when the covers tightened. Let's replace one glass cover with a paper diaphragm. The noise gives us some idea of the forces that may occur inside approved equipment. Explosion-proof equipment is designed to withstand internal explosions. Let's see why flame or heat does not escape. Threaded, serrated, or ground joints are used. The flange must be wide enough to cool the gases when the bolts are tight. The clearance between the cover and the box must not exceed specified tolerances, so that any escaping gas or particles will be cooled below the ignition temperature of the surrounding atmosphere. This approved switch box is sealed in the glass chamber and attached to the conduit. Both the enclosure and the glass chamber are filled with the same flammable atmosphere. The explosion in the switch box does not ignite the mixture in the chamber, even though the mixture is flammable. Let's loosen one bolt and see whether flame will escape. You can see how important it is to keep all bolts tight. Great care should be taken to preserve the tight fit of the two surfaces of a ground joint. Sand, gravel, and other foreign materials can destroy the snug fit of the surfaces between the flanges, through which heat can travel out of the fixture. If a workman uses a screwdriver to break the cover loose from the fixture, he may gouge the surface of the metal. Anything that destroys the snug fit of the surfaces may permit flame to pass and ignite gas on the outside. This approved enclosure has a threaded cover. To be approved, covers must have at least 5 threads in contact. The enclosure is placed in a flammable atmosphere. The explosion did not ignite the mixture on the outside, which you can see is flammable. A threaded cover should never be so tight that it may be damaged when it is removed. The cover should be just tight enough to prevent vibration from loosening it, tight enough to prevent a curious person from unscrewing it by hand. The pressure ahead of the flame pushes the threads against each other. The hot gases, having to travel around and around through the space between the threads, are cooled to below the ignition temperature of the mixture on the outside. To prevent flame travel through conduit or out of an enclosure, a seal is installed within 18 inches of each arcing device, or wherever conduit enters or leaves a hazardous area. This explosion gives you some idea of the force that is exerted against the seal. Now the seal is closed, as it would be in a plant. If the seal fails, you'll see a little dust or flame. The seals in this equipment have stopped several hundred such explosions. Because equipment approved by the Bureau of Mines uses approved cables instead of conduit, packing glands are used to isolate each arcing device. Explosion-proof equipment is not vapor tight. Atmospheric changes cause it to breathe. Moisture accumulating in the enclosure can cause an electrical fault. To minimize condensation, breathers are used. This breather, one of several approved types on the market, is a loose, threaded device. When one of these breathers is placed in the top and another at the bottom of an enclosure, the threads are so loose that air circulates and the condensed liquid drains out of the bottom breather. When an explosion occurs in the enclosure, the threads of the breather function the same as a threaded cover. We have seen flame travel through 3/4-inch conduit with 2 wires. But will flame travel through conduit if it contains the maximum number of wires specified by the electrical code? An electric light bulb is not generally considered an arcing device, but explosions have occurred when a bulb has become loose or has been broken. The glass globe of an explosion-proof light fixture is sealed in a metal ring. The fixture is designed and constructed to withstand an internal explosion. As you can see, the flash is very bright. This so-called vapor-proof or vapor-tight light fixture is not vapor-proof nor explosion-proof. The threads are molded on the glass of the globe and are not designed to prevent flame from passing them. It should not be used in hazardous areas. Yet you often see this type of globe on the outside of a door leading to a hazardous area where a flammable mixture could accumulate in it. Let's ignite the same mixture in it as we did in the explosion-proof globe. A single unapproved piece of equipment can nullify or neutralize all the safety of explosion-proof or permissible equipment. Unapproved hand drills and extension lights are the greatest offenders. The use of these or any other pieces of unapproved electrical equipment, including unapproved drinking fountains, should require the same permits or precautions as electric welding equipment. From these demonstrations, we should all have a better understanding of how flame in a confined space travels. We should have a better understanding of flammable limits, flame speeds, and pressure piling. When a blue flame is burning at the end of a pipe or hatch of a tank, it means that the pipe or tank contains a flammable mixture. Cutting off the fuel may cause an explosion. When a luminous flame is burning, the fuel supply can be cut off because the mixture in the pipe or tank is above the upper flammable limit and will not burn. Many forces and counter forces develop during an explosion. Sometimes an explosion blows out, and sometimes it sucks in. Flammable dust can be just as dangerous as flammable gas. Explosion-proof or permissible equipment is vitally necessary in hazardous areas. Approved electrical equipment will withstand an internal explosion, and it will not permit enough heat to escape to ignite flammable gas on the outside. Explosion-proof equipment is constructed without gaskets in joints. The surfaces are machined to close tolerances of a few thousandths of an inch. All approval plates should be checked to make sure that all equipment is being used in the class of area for which it was approved. Proper maintenance is as important as proper equipment. Never gamble with your life or with the lives of your fellow workers. Play it safe by using correctly maintained electrical equipment. If you don't,